Hi everyone, and welcome back to another AP Calculus video. For this video, I'm going to ask you to step back in time with me, back to a time before we had fancy graphing calculators, before we had cell phones, before we had Desmos and computers and things that would crunch our numbers for us. And I want you to picture, if you will, mathematicians all across Europe doing their work, writing letters to each other, not by the light of a light bulb, but by candlelight, trying to figure out how to evaluate complex functions like square roots, sines, cosines, natural log, exponentials, things like that. And they didn't have fancy calculators. They couldn't estimate. And so, estimation was tricky at best. So think about this. If I asked you to tell me the square root of 1, you would know that it was 1. And the mathematicians back in, 16th, 17th, 15th century Europe knew what the square root of 1 is. They also knew what the square root of 4 was. They knew that it was 2. And so they could, at best, estimate that the square root of 2 and the square root of 3 were somewhere between 1 and 2. And they had ways to maybe evaluate to some decimal point, some decimal value. But to really get a reasonably quick estimation, that was something that they didn't have the capability of doing until calculus came around. And so I'm going to ask you to venture with me and do some problems without the use of technology and think about how amazingly revolutionary this process that we're going to learn today was when it was first discovered and developed. So let's go back in time. So here we are, and here's the function we want to evaluate. We want to think about the graph of y equals the square root of 1 plus x. Now, to us here today, this may not be a terribly complicated function. We just graph it in our calculator, and we can find out anything. We can even find the derivative. But back in the 1600s, when calculus was being developed by candlelight, remember, finding and evaluating a function like this one was not as easy. And so let's say that we wanted to evaluate for x equals 0.1, some value. We'd be looking essentially for the square root of 1.1. Well, what is that? We don't know. But then Isaac Newton and Gottfried Leibniz and all the other fathers of calculus, and I'm sure that there were some women in there too, but probably not as many because, that's how it was in those days. But those who were developing calculus and exchanging these ideas came up with this way, and they said, well, you know what, when I look at this graph and I zoom way in, something interesting happens. So let's take a peek at the graph and see if we can see what they saw. So here's my trusty pal Desmos, and here's the graph of the function. Now, on a normal scale, it looks to be like a curved square root function, something we're very familiar with, no surprises here. And I'm even going to plot the actual value. So Desmos will tell me that this point at 1.1, here's my 3 decimal approximation, 1.049, or the actual value is 1.0488, 08848, blah, 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 blah. So in any case, this is what we can do here today. But how does Desmos do this? What's the algorithm that our calculators are programmed with to be able to spit these values out? Well, some of them are based on what we're going to talk about today. So let's take a look at what happens when I zoom way, way in. The further in I go on this function, and notice the scale along the top and the bottom, the sides and the bottom, we're zoomed way, way, way in. And I'm hoping that you'll notice what I notice, and that's that this function is beginning to resemble a linear function. And this function, when we zoom in, and most functions are this way, when you zoom way in, you have what's called local linearity. That means up close, it looks like a line. You have to zoom way in, and it looks like a line. Now, if we zoom way out, there's no global linearity. The only thing that has a global linearity is a linear function. But locally, when I zoom way, way, way in, really close to this point, it looks like a line. So those who were developing calculus and trying to find better ways to evaluate functions, because that was the big question, is how do I find the square root of 1.1? They didn't have phones or Snapchat or other games or anything like that. They didn't have those distractions around them. So these people were thinkers. They sat back and said, well, how can I find a better way? And thank God for that, because if we didn't have people who sat around and thought about how to solve problems that we didn't even know exist, we wouldn't be able to do fun things like calculus. So when I look at this, I see a line. And so did they. And then they said, well, how do we solve this problem? How can we at least estimate? Can we get close? Because estimation is better than nothing. So they said, well, if it's a line, I wish I could write the equation of a line that was similar to this. And wouldn't it be true that if I could write the equation of the line that's tangent to that point, that I could just plug the number into that line and they would share that point? And that would be true. But the problem is we can't evaluate that function because that function is going to have that slope when I try to find that tangent line at 1.1. I'm going to run into the same problem that I have with this function because the derivative is going to involve the original function. And so they said, well, what if instead of writing it at that point, what if I wrote a tangent line that was really close to it? Somewhere where I can evaluate. Because remember, to write the tangent line, you not only need the slope, which is the derivative, but you also need a y value. So you need to be able to plug x in and get a y back. And so as you're looking at this function, I have the square root of 1 plus x. Well, numbers that are really close to 0.1 would be something like 0. 0 is really close to 0.1. And when x is 0, by golly, I can evaluate f of x. It's just 1. I can get a y value. So what I'm going to do is I'm going to back this up and I'm going to write a line that's tangent not up here at the point in my problem, but I'm going to write a tangent line down here. And it's going to be tangent at the point 0, 1. And when I do that, it's going to look really, really similar. And so let me show you what I mean. Here's my tangent line. It's blue. And if I can zoom way in, see here I'm tangent at the point 0, 1. Okay, and this is the equation. We'll show you where that comes from in just a moment. But here's my tangent line where I found my derivative at 0. I found my y value at 0. I graphed the tangent line and take a look. When I get really close to this point in question, the tangent line, it's not exact, but man, is it close. Because check it out. There's the estimation, that blue dot right there. And if I zoom in and label what those points are, remember, here's my actual value, right? So we'll label that actual value of y. Here's my linear estimation using the tangent line to a point super duper close, right? We want 0.1, so we backed it up and we use 0 because we can work with 0. We can't work with 0.1. And so here's my linear estimation. Check it out. On my tangent line, I estimate at y at 1.05. Here, it would round to 1.05. So I'm within like 2 places of accuracy. Well, 1 place of accuracy, almost 2. Now that's pretty darn good. And for the times when we didn't have power, we had no calculators, we had no Desmos, this is a pretty good estimation, and it was a pretty exciting find. So let's back up and let's see how it is that we came up with our equation for our tangent line and how we used it to estimate our function at 1.1. So here we are back at our function, and what we wanted to do is we said, okay, we want to know something about 0.1. So we're going to write a tangent line at 0, which is really close to 0.1. And to do that, I need a slope and I need a point. So I'm going to use x equals 0. All right, so my point was really easy. It's just y equals the square root of 1 plus 0. So the point was 0, 1. And then my slope used the derivative. So f prime of x was 1/2 times 1 plus x to the negative 1/2. Chain rule, the derivative multiplied by the derivative of the inside is just 1. So here we go. F prime of 0, the slope of this tangent line at 0 is 1/2 times 1 plus 0 to the negative 1/2. That's just 1/2. So my tangent line that I just graphed, and we'll verify this, we'll go back and look at it, was this. Y minus 1 equals 1/2 x minus 0. And when I solve for y, I get y equals 1/2 x plus 1. So that's my equation of my tangent line, and I used it because check it out. I can take now and I can plug in, I can estimate f of 0.1 is approximately, and instead of a y, just to set things apart because I have a y going on in the original, I'm going to rewrite this as I'm going to say it's the linearization. So I'm going to use a little bit different technique, and I'm going to call this L of x. So it's this new function, L of x, right? So I'm going to say it's approximately L of 0.1, which when I plug that in, I get 1/2 times 0.1 plus 1. I can have that. That's 0.05 plus 1, and that's where my 1.05 came from. So the linearization on the line is equal, but f of x is approximately 1.05. So we're approximating f of x using this new linear function, which is just the equation of the tangent line, L of x. Okay? So here's what we just did. We wrote the equation of the tangent line at x equals 0. We chose 0 because it was super duper close to the point we wanted to know about. This L of x function can be used to approximate a point that's super close to my point of tangency. So the further I get, the more off my function is going to be. So let's go back to our function and look at what's happening. So here I tried to estimate 0.1. If I tried to estimate a value that was even further away from 0, so remember that point of tangency, let's refer to that as our center. So now our linearization is centered at x equals 0. Notice I could go forward or backward. So like I could even estimate somewhere negative on the other side of 0. And look, the blue and the red lines, the closer they are, the better my approximation will be. But the further apart they go, the worse it's going to be. So now the point being, if I want to estimate a point that's further away, I might want to choose a different center. In other words, I might have to rewrite my linearization, rewrite that tangent line, and pick a different point of tangency. So to demonstrate this, let's take a look. So I'm going to turn a couple of these functions off and reset my Desmos. So here what I have is just a kind of an example to show you that if I want to pick a different point, I'll need to rewrite my equation of my line. And so we're going to just use the visual difference between the linear estimation and the actual point to demonstrate just how far off you can get the further away you are from your center. So the way I have it set up is that the green line is our linearization. So just pay attention to that green line. And then we have this A value. A is where we're going to center things. So right now we have it centered at 0. So where x is 0, that's going to be where my tangent line. So this is exactly what we had in the example that we just did. So as I move though, suppose I want to estimate where I have an x value of 0.2. Well then my linear estimation, check it out, it's getting further and further and further away. So if I want to plug in 1, I've just now created a situation where look how far away that is. I mean, my actual point is something like 1.4 something, whereas my linearization is at 1.5. So it's getting way off. But if I move my center by 1, so let's move my center, all of a sudden my actual and my linear become the same thing. And now I can go on and estimate points that are a little further away. So this would be like 1.4. So this is like plugging in 1.5. So what's the square root of 1.5 plus 1? That's what this is estimating. And so the further away you get, you're going to have to adjust and rewrite your equation of your tangent line. You always want to pick a point to center your tangent line at that's close to where you want your linear estimation. Now, this will work for just about any function. So you could plug in any function of f or any function of x that you want and be able to demonstrate this linearization. For example, natural log of x. This is a function that you wouldn't have been able to evaluate without a calculator. It just took so much brain power to try to evaluate it. But if we take this same function and graph the equation of the tangent line, so suppose we want to evaluate, let's center our tangent line at 2. Now we can evaluate numbers like 2.3, 2.4, numbers that are close. And the further away we get from that center, the more off our estimation is, the further away from the actual value we become. So this works no matter what function you have. You just need to find the equation of the tangent line. And generally, we just take that equation and we put it into slope-intercept form. And instead of saying y equals, we just say L equals. and that shows that we're using it to estimate using the linearization. So let's see what this example looks like, and we'll try a couple of little examples just to make sure we're comfortable with the concept. So here we're going to use linearization to estimate f of 0.2 for f of x equals e to the 2x. So we want to write the equation of the tangent line for a point really close to this value. Now most of the time the problems will specify, use the linearization, they'll say at x equals 0. But what we want to understand is that in the real world, you know, Isaac Newton, he had to pick his own value. And so if the problem doesn't say, you need to pick a value that's close to the point. So here we're going to use x equals 0. So what we need to do is write the equation of the tangent line. So here we go. We need a point. We need a x, y. So that x is going to be 0, and then the y value is going to be e to the 2 times 0. That's going to be 1. So my point is 0, 1. Now I need a slope. That's the derivative. So f prime of x is going to be e to the 2x times 2, because the chain rule says multiply by the derivative of that exponent. So 2e to the 2x, f prime. Now we're going to find f prime of 0. That's going to be my slope. 2e to the 2 times 0 is 2 times 1, which is 2. So my equation is going to be y minus 1 equals 2 times x minus 0, or y equals 2x plus 1, and then I just rewrite it with an L. That's all. So now I'm showing, hey, this is an application. I'm taking this tangent line. L means it's the linearization. So now L of 0.2 is 2 times 0.2 plus 1, which is 0.4 plus 1, which is 1.4. So this is approximately f of 0.2. And if we were to test it out and just either look at the graph or plug it into our calculator, here's what we would get. The actual value is 1.492. So this one's a little bit more off, and let's take a look at why that is. Now when we look at the graph in Desmos, remember the red curve is the actual e to the 2x function. The green curve is our equation of our tangent line. And so we can see our linear estimation came in underneath. The actual value is a bit higher. And we can see that it's because of the curvature of our function. So that e to the x function, the way that it grows, it just gets steeper and steeper. And so that has an impact on just how accurate our function is. So we're not going to have the same degree of accuracy when we're using a linearization to represent a function. And as a matter of fact, linearization is it's the beginning steps of finding something called a Taylor polynomial to represent a function, and that's a BC topic that we'll get into in Calc BC. But we're going to learn that a linear function is not going to give you the same degree of accuracy. If we can rewrite it maybe as a different kind of a function with more terms, we can actually get a higher degree of accuracy. And one of the topics in BC is exploring just how accurate is our representation, is our estimate of these functions using polynomials, which a linear estimation is a form of a polynomial. It's a form of it is a Taylor polynomial to some degree. So maybe not a Taylor polynomial, but it's a polynomial representation. So the idea here is that sometimes we're going to be over, sometimes we're going to be under in our estimate, and it really depends on the curvature. And so if I think about what's happening here, this curve is concave up. And when we have a curve that's concave up and we write our tangent line, that tangent line is always going to come in under the curve. When we have a curve that's concave down, like our first one, our estimate was actually over top. And that has to do with the fact that your linear function is going to be coming in either above or below. So a better way to look at this is when we think about it, let's draw a little picture. Our approximation will overestimate when our curve is concave down. And so if this is my original function, wherever my estimate is, if I'm trying to estimate right here, well, I'm going to come in above. So we overestimate when the curve is concave down. We're going to underestimate when our curve is concave up. And that has to do with, if this is the curve, my tangent line will always come in underneath. Okay, so if this is what we're going for, we're always going to be below. So that's a good way to think about it. I always just draw a picture. I'm not good at memorizing. Now, the last thing that I want to talk to you about here in this video is something called a differential. Because when we talk about a line and when we talk about estimating, another thing that we want to estimate is we want to talk about, well, let's say that on the graph, if I estimate using the linearization at point 1, what if I move it up to point 2? How much can I expect that y value to change? So if up here we got our estimation, this was our original function, if up here we were estimating at 1.05, let's say I wanted to find L of 0.2, and I change my x value by increasing it by 0.1. If I change x by 0.1, how much will y change by? And that's a valid question. And what we're talking about here is something called a differential. And a differential says if I increase x by a certain amount, what's my estimate of what y will increase by? And so a real world example here is talking about, like, for example, if the speed in your car is 60 miles an hour, each hour you drive, you would expect to see a change in your position of 60 miles. That's a differential. So as you change x by a certain amount, how much do you expect the distance to change? Well, you're not going to go 60 miles per hour consistently. It's based on an average. You're making an estimation. You're saying, well, we expect to see you go 60 miles. So when you call me and you've only gone 5 miles in an hour, I know that something is up, right? So usually when we talk about differentials, we talk about a change in x that's really small. So we wouldn't be talking about an hour in time unless that hour is a small amount compared to our whole big picture. So a better question might be, in 1 minute or 1/60th of an hour, what would we expect our change in position to be? So let's take a look, and that number would be a lot smaller, right? So in a minute, if you're going 60 miles per hour, how many miles would you expect to change? So that would be a more likely question. So we want a small change in x. So here's a better example. So let's look at a real world example. Suppose we have this nice polynomial, x to the 5th plus 37x. When x is 2, if dx, so that means the change in x, right? So that would be like, hey, after an hour has gone by. So after x has gone up by 0.0 or 0.5, what do we expect y to be up by, or down for that matter? So let's see how we solve this. The idea here, and it's real easy if we think about it in terms of derivatives. If y is f of x, then dy dx is f prime, right? So let's highlight this. If y is f, then dy dx is f prime. So let's find dy dx. dy dx is 5x to the 4th plus 37. So if dx is 0.05, okay, so here we go, dy over 0.5, I keep saying too many zeros, equals 5x to the 4th plus 37. And then we also want to note that it's when x, oh yeah, see, look, I did have a little typo. That's probably what it is. We're going to change that to 0.05. There we go. That's a more reasonable amount to see a change in. Okay, so when x equals 2, then what we need to do is we need to put 2 in, because this is at a spot. Because at every x, it's going to be different, right? If the curve is getting steeper, then the amount of change is going to be much different than when the curve is flat. So the idea here is we're going to say dy over 0.05 equals 5 times 2 to the 4th plus 37. Okay, well, 2 to the 4th is 16. 5 times 16 is 80, so that would be 117. Well, that's dy over 0.05. You guys, we want to know what dy is, so guess what? Solve for dy. So here we go. dy equals 117 times 0.05. So essentially we're just kind of solving, and then this is the point when we would go ahead and pull out our calculator and go ahead and get the decimal value, 5.85. So if we increase x by 0.05, then we expect y to go up by 5.85. So Let's see if we can demonstrate that by showing you a couple of values, and then that'll bring us to a close here. So if f of 2, when we plug it into our original equation, is 106, we just discovered that if we increase that by 0.05, so we're going to be looking for f of 2.05, that we should expect the y value from 106 to increase by 5.85. So when we add 5.85, we get that f of 2.05 is estimated to be approximately 111.85. Now this is just another estimation tool, right? So back in the day, we had candles, no calculators. This is our estimation of 2.05 because that's the change in y that we expect to see. Here's the actual value. F of 2.05, when I plug the number in, I get 112.055. So that's a difference of about 0.2, okay? So I got pretty close with my estimation. So again, all I do, and let's sum this up so in case you ever have to find a differential, here's what we found. We said, well, if y equals f of x, then dy dx is f prime. If we know what dx is, that's the increase in x. We're looking for what the increase in y will probably roundabout be. Remember, it's not an exact science. This is an estimation technique. dy is going to just be the derivative at x times the change in x. You'll always be given dx. Another way to write it is this, delta x. You'll always be given dx. You'll always be given a function, and you'll always be told what x is. So here, just to recap, here was my f prime of 2. Right? So this was f prime of 2. And then over here, this is where I multiplied by dx. So here's my f prime of 2 times my dx. That's where I got my dy from. So using that formula, this is what we applied, this is what we discovered, and this is how you're going to apply it should you ever be asked about differentials. So again, these are estimation techniques. They're techniques that we use when we don't have a calculator handy. We use our calculator to verify our findings, but this is what they did in the 1600s. So think about that for a little bit and understand what an amazing feat it was to, number one, discover that you could estimate a curve using a local linearization, which is just your tangent line with an L instead of a Y. And then also talking about how we can estimate, well, if I increase x by a little bit, what's the change in y going to be? So these are pretty fantastic estimation techniques, and I hope that even if you don't ever use them or you don't appreciate them, you can at least appreciate the significance of the discovery back in the 1600s. So my encouragement is just keep at it. Make sure you guys are taking good notes. Refer back to your notes always, and just keep trying. You've got this.